there is something worth considering. Something that's true right now as you're listening to this. The atoms that make up your hand, the ones in your breath, in every cell of your body, most of them are older than the ground beneath you. Older than the oceans, older than the mountains, older than the earth itself. And many of them are older than the sun. This isn't metaphor or poetry. It's measured, verifiable fact. You're listening to The Drowsy Astronaut, and over the next while we're going to follow a quiet thread through time, back through billions of years, to find out where the material that makes you actually came from. There's no rush to get anywhere. This is a slow journey through the cosmic perspective, and if you're settling in for the night, wherever you are, just know that you're exactly where you need to be. And if you find something in this worth staying with, a like or a subscribe really helps this keep going. Without further ado, let us begin. Your body, right now, is made of atoms. Somewhere around 7 octillion of them, a number almost too large to think about. These atoms are arranged into molecules, proteins, DNA, all the structures that make a living thing. But the atoms themselves, the basic building blocks, they're not new. They weren't created when you were born. They existed long before. An atom is a nucleus, protons and neutrons bound together, surrounded by a cloud of electrons. The electrons can be exchanged, shared between atoms in chemical reactions, but the nucleus remains. It's stable, often for billions of years, and it's the nucleus that carries the atom's age. Because the nucleus was made at a specific time, in a specific place, under specific conditions. Every nucleus has a birthday and a birthplace. The hydrogen in your body, about 10% of your mass and more than half your atoms, those nuclei are nearly 14 billion years old. They formed in the first few minutes after the Big Bang, when the universe was still a sea of energy and particles, cooling and expanding. Every hydrogen nucleus in the water you drink, in the organic molecules that make your cells, is primordial. Older than any star, any galaxy, any structure in the universe. The carbon in your body, about 18% of your mass, the element that forms the backbone of every organic molecule, that carbon was made inside stars. Not the sun, but earlier stars. Ones that lived and died before the solar system existed. Carbon nuclei form in the cores of stars, where temperatures reach hundreds of millions of degrees, where helium nuclei collide and fuse together in a process that requires precise conditions. The carbon in your hand right now was forged in stellar fire billions of years ago. Oxygen makes up about 65% of your body by mass, mostly in water but also in proteins and other molecules. Oxygen nuclei form in massive stars, larger than the sun, in the late stages of their lives when their cores are hot enough to fuse carbon into heavier elements. The oxygen you breathe, the oxygen in your blood and bones, came from stars that no longer exist. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of these were made in stars and scattered into space when those stars died. Some of those deaths were quiet, shedding outer layers gently into the void. Others were violent supernovae that outshone entire galaxies for a few weeks before fading. Either way, the heavy elements in your body came from stars that exploded or dispersed before the sun was born. This means that you are, physically and literally, made of material older than the planet you're standing on. Earth formed about 4.5 billion years ago, from a cloud of gas and dust, and that cloud already contained hydrogen from the Big Bang, carbon and oxygen and iron from dead stars. Those atoms drifted through space, sometimes for hundreds of millions of years, before gravity pulled them together into the disk that became the solar system. The atoms in your body have been on Earth since its formation, cycling through rock and water and air and life. A carbon atom in your hand might have been in a dinosaur once, in an ancient fern, in volcanic gas, in a drop of rain that fell 1 billion years ago. Atoms are recycled endlessly on Earth. They move from the atmosphere into the ocean, into living things, into soil, into rock, and back again. Nothing is wasted. Nothing is truly new. But before they were on Earth, before they were part of the solar system, these atoms were somewhere else. They were in the cores of stars, or drifting through the interstellar medium, or locked in clouds of gas light years across. They have traveled, not metaphorically but literally, across vast stretches of space and time to arrive here, to be part of you temporarily. You are not separate from the universe. You are made from it, from its oldest materials, gathered and arranged into a form that can think and feel and wonder about its own origins. Every breath you take contains atoms that have been cycling through the Earth for billions of years. Every thought you think runs on structures built from elements forged in stars that died before the sun ignited. This is the reality we live in, though it's easy to forget. We experience ourselves as separate, as individuals distinct from the world around us. But at the atomic level, there is no separation. The boundary between you and the environment is temporary and porous. You exchange atoms constantly with the air, with food and water, with everything you touch. The atoms that make you today are not the same ones that made you 7 years ago. You are a pattern, a process, not a fixed thing. The atoms flow through you and you persist as a shape they take for a while. And these atoms, the ones currently part of you, have histories. They carry information in their nuclei about where they formed and when. Scientists can trace the origins of elements by studying the conditions required to create them. The temperatures and pressures and reactions that build one nucleus from others. We know that hydrogen came from the Big Bang, because only in the hot, dense, early universe could protons survive and remain free. We know carbon came from stars, because only in stellar cores are temperatures high enough for helium fusion. We know that elements heavier than iron came from supernovae, because normal stellar fusion can't create them. They require the extreme conditions of a stellar explosion. This isn't speculation, it's physics confirmed by observation. We can look at the light from distant stars and see the signatures of these elements in their spectra. We can measure the abundances of elements in meteorites, in the sun, in interstellar clouds, and see the patterns that stellar nucleosynthesis predicts. We can watch stars explode and see them brighten because of the radioactive decay of freshly forged heavy elements. The story of where your atoms came from is written in the universe, in starlight and stone, in the ratios of isotopes and the distribution of elements across space. But knowing the science doesn't diminish the wonder of it. If anything, it deepens the connection. You are not just like stardust in some poetic sense. You are actually made from the ashes of stars. The iron in your hemoglobin, the protein that carries oxygen in your blood, that iron was created in a supernova explosion billions of years ago. It was blasted into space at thousands of kilometers per second. cooled as it expanded, mixed with clouds of hydrogen, drifted for eons, eventually fell into the gravitational well of the forming solar system, accreted into the early Earth, cycled through the planet's interior and crust and biosphere, and finally ended up in your blood, allowing you to live. That journey from stellar core to your body took longer than the Earth has existed. The atoms in you are travelers from deep time and deep space, and you are a temporary arrangement they've fallen into on a small planet, orbiting an ordinary star in an unremarkable part of the galaxy. There's something quietly profound in that. You are ancient and new at the same time. Your body is young, a few decades at most, but the material you're made from is billions of years old, older than almost everything you can see or touch. You are a brief flicker of organization in the long, slow flow of matter through the universe. And you're not alone in this. Every person you've ever met, every living thing on Earth is made from the same ancient stellar material. We share not just a common ancestry in the biological sense, but a common atomic heritage. The carbon in your body and the carbon in a tree outside came from the same sources, forged in the same kinds of stars, scattered by the same kinds of events. We are all made from recycled stardust, rearranged into different forms, temporarily separate but fundamentally connected. This is the story we'll explore, not quickly or urgently, but carefully, following the thread back through time. We'll see where each element in your body came from, how it was made, how it traveled through space to reach Earth, and how it ended up part of you. The journey goes back nearly to the beginning of everything, and forward to this moment, right now, as you listen and breathe and exist as a temporary sculpture made from the universe's oldest materials. Most of your body is water, about 60% by mass, more in some tissues, less in others, but water is the majority of what you are. And water is hydrogen and oxygen, two hydrogen atoms bonded to one oxygen atom, H2O, a molecule so common and essential that it's easy to take for granted. But the hydrogen in that water, in every water molecule in your body, is almost 14 billion years old. Hydrogen nuclei are simple. A single proton, nothing else. One positively charged particle, the lightest and simplest nucleus possible. It orbits a single electron, making a complete hydrogen atom. But the nucleus, the proton itself, that's what carries the age. And those protons are the oldest things you contain. They formed in the early universe, in the first few minutes after the Big Bang, when the cosmos was unimaginably hot and dense. At the very beginning, in the first fractions of a second, there were no atoms at all, not even nuclei. Matter existed as a quark-gluon plasma, a state so energetic that protons and neutrons couldn't hold together. But as the universe expanded, it cooled. And as it cooled, quarks began to bind into protons and neutrons. By the time the universe was about 1 second old, it was cool enough for protons and neutrons to survive. Over the next few minutes, some of these protons and neutrons collided and stuck together, forming the first atomic nuclei. Deuterium formed, a proton and neutron bound together. Some deuterium fused into helium, 2 protons and 2 neutrons. Tiny amounts of lithium formed as well, but most of the protons remained alone, unbonded, too spread out, and too cool to fuse with anything. This process, called Big Bang nucleosynthesis, lasted only about 20 minutes. After that, the universe had expanded and cooled too much for fusion to continue. What remained was a sea of hydrogen nuclei, about 75% by mass, with helium making up most of the rest, and trace amounts of deuterium and lithium. No heavier elements, no carbon, no oxygen, no iron, just hydrogen and helium, drifting in an expanding, cooling universe. For hundreds of thousands of years, the universe was too hot for atoms to form. Electrons couldn't bind to nuclei because photons kept knocking them free. But eventually, about 380,000 years after the Big Bang, the universe cooled enough for electrons to settle into orbit around nuclei. Hydrogen atoms formed, and the universe became transparent to light for the first time. That light, stretched by cosmic expansion, is still visible today as the cosmic microwave background, the afterglow of the moment atoms came into being. Those hydrogen atoms, formed in the infant universe, are the same hydrogen atoms that exist today. Protons don't decay, at least not on any timescale we've observed or predicted. They're stable, essentially immortal. The hydrogen nucleus in a water molecule in your body right now is the same age as the universe itself, unchanged since the first minutes of creation. When you drink water, you're drinking something made from the universe's first element. Every sip contains protons that are 13.8 billion years old, that existed before stars, before galaxies, before any structure at all. They've been part of clouds and stars and planets, part of oceans and ice and living things, but the nuclei themselves haven't changed. They're primordial. There's a certain stillness in that. Hydrogen is simple, stable, ancient. It makes up about 10% of your body by mass, but nearly 60% by number of atoms. Because hydrogen nuclei are so light. Most of that hydrogen is in water, but it's also in fats, in proteins, in DNA, in almost every organic molecule. Life is built on a framework of carbon. But hydrogen is everywhere in that structure, bonding to carbon and oxygen and nitrogen, filling out the molecular shapes that make biology possible. And all of it, every hydrogen atom in you, is a survivor from the universe's beginning. These protons have witnessed everything. They existed when the first stars formed, a few 100 million years after the Big Bang. They were there when galaxies assembled, when the universe transitioned from smooth to structured. They drifted through the voids between galaxies, fell into star-forming clouds, became part of stars and planets and living things, and now they're part of you, temporarily, until you return them to the world, through breath and sweat and eventual decay. Hydrogen is the most abundant element in the universe, making up about 75% of normal matter. It's the fuel stars burn, fusing hydrogen into helium in their cores, and releasing the energy that makes them shine. The sun fuses about 600 million tons of hydrogen into helium every second, a process that's been ongoing for 4.6 billion years and will continue for another 5 billion. When the sun eventually exhausts its hydrogen, it will swell into a red giant, fuse helium into carbon and oxygen, and then shed its outer layers, leaving behind a white dwarf, slowly cooling in the darkness. But the hydrogen itself, the nuclei, they don't disappear. When hydrogen fuses into helium, the protons combine with neutrons to form a more complex nucleus. But if helium is broken apart, either by high-energy collisions or in certain stellar processes, protons are released again. Hydrogen can be consumed and recreated, locked into heavier elements and freed again. The universe recycles it, just like it recycles everything else. The hydrogen in your body has likely been through this cycle. It may have been part of earlier stars, fused into helium and then released again when those stars died. It may have drifted free through interstellar space for billions of years, never incorporated into a star at all. Some of it might have been part of the solar nebula from the beginning, primordial hydrogen that never saw the inside of a star until the sun formed. There's no way to know the individual history of a particular proton, but we know the collective history, the journey, that hydrogen as a whole has taken through cosmic time. And that journey has led here, to Earth, to water, to you. The hydrogen in your cells is the same substance that filled the early universe, that fuels the stars, that makes up the vast majority of visible matter. It's the simplest element and the most fundamental, the starting point for everything else. But hydrogen alone isn't enough to make you. It's essential, abundant, ancient. But life requires more than hydrogen and helium. It requires carbon for structure, oxygen for energy, nitrogen for proteins, phosphorus for DNA, calcium for bones, iron for blood. All of these elements are heavier than helium, and none of them were made in the Big Bang. They came from somewhere else. They had to be built, atom by atom, nucleus by nucleus, in environments far more extreme than the early universe. They came from stars, from the fusion reactions in stellar cores, from the collapse and explosion of massive stars at the end of their lives. Your body is mostly hydrogen and oxygen by atom count, but by complexity, by function, by the richness of chemistry that makes life possible. It's the heavier elements that matter. And every single one of those heavier elements was forged in a star, sometimes billions of years before the sun existed. That's the next part of the story, the part where simplicity gives way to complexity, where the universe learns to build elements heavier than helium. It happens slowly, over millions of years, inside stars scattered across the galaxy. It happens through fusion, the process that powers stars and constructs the periodic table, one nucleus at a time. The hydrogen in you is ancient, primordial, a relic of the universe's birth. But the carbon, the oxygen, the calcium, the iron, those are stellar. They're younger than hydrogen, but still billions of years old, made in stars that no longer exist. And understanding how they formed and how they ended up in you means understanding what stars are, what they do, and what happens when they die. Stars are more than lights in the sky, they're furnaces, places where atomic nuclei are forged from simpler ones, where the periodic table is built step by step through fusion. Every element heavier than helium in your body was made inside a star, and understanding that process means understanding how stars live and die. A star forms when a cloud of gas, mostly hydrogen with some helium and trace amounts of heavier elements, collapses under its own gravity. As the cloud contracts, it heats up. Gravitational energy converts to thermal energy, and the core of the forming star becomes hotter and denser. Eventually, if the mass is sufficient, the core reaches about 10 million degrees, and hydrogen fusion begins. Hydrogen fusion is the process that powers most stars, including the sun. At these extreme temperatures, hydrogen nuclei, protons, move fast enough to overcome the electromagnetic repulsion between their positive charges and collide with enough energy to stick together. Through a series of reactions, 4 protons are converted into one helium nucleus, 2 positrons, 2 neutrinos, and energy in the form of gamma rays. The energy released is what makes the star shine, producing the heat and light that radiates into space. This process is called stellar nucleosynthesis, and it's how stars create heavier elements. Fusion releases energy when the product nucleus is more stable than the starting nuclei. For elements lighter than iron, fusion releases energy, so it can happen spontaneously once the temperature is high enough. For elements heavier than iron, fusion requires energy input, so it only happens under special circumstances. A star like the Sun will spend most of its life, about 10 billion years, fusing hydrogen into helium in its core. During this time, the core gradually fills with helium, a byproduct that doesn't fuse at the core's current temperature. Eventually, the hydrogen in the core runs out. Fusion stops, the core contracts and heats up, and hydrogen begins fusing in a shell around the core. The outer layers of the star expand and cool, turning the star into a red giant. If the star is massive enough, the core eventually becomes hot enough, around 100 million degrees, for helium fusion to begin. Helium nuclei, also called alpha particles, fuse together in a process called the triple alpha process. 3 helium nuclei combine to form 1 carbon nucleus. This process is delicate, requiring precise conditions and a fortunate quirk of nuclear physics. If the energy levels in carbon nuclei were slightly different, the reaction wouldn't proceed efficiently, and carbon wouldn't form in large quantities. But the levels align, and carbon is produced. Once carbon exists in the core, further fusion becomes possible. Carbon can fuse with helium to form oxygen. In more massive stars, where core temperatures rise even higher, carbon can fuse with carbon to form neon, magnesium, sodium. Oxygen can fuse with helium to form more neon. Neon can break down and recombine to form heavier elements. Each stage of fusion requires higher temperatures and shorter timescales. A star might burn hydrogen for millions or billions of years, helium for hundreds of thousands of years, and heavier elements for just years, days, or even seconds. The sequence continues in massive stars, those with at least 8 times the Sun's mass. These stars have cores hot and dense enough to fuse elements all the way up to iron. Silicon fuses into iron in the final days of a massive star's life, creating a core of iron nuclei surrounded by shells of lighter elements still undergoing fusion. This layered structure resembles an onion, with hydrogen burning in the outermost shell, then helium, carbon, oxygen, neon, and silicon in successive inner layers, and iron in the core. That iron is the end of the line. Iron nuclei are the most stable, the most tightly bound. Fusing iron into heavier elements doesn't release energy, it requires energy. So when a massive star builds up an iron core, fusion stops. There's no more energy source to hold the core up against gravity. The core, now unsupported, collapses. This collapse happens fast, in less than a second. The core, roughly the mass of the Sun but compressed into a sphere the size of a city, implodes. Electrons are forced into protons, forming neutrons and releasing neutrinos. The core becomes so dense that neutrons themselves resist further compression, and the collapse halts abruptly. The infalling material rebounds off the now solid neutron core, and a shockwave races outward through the star. This shockwave, carrying enormous energy and driven by the flood of neutrinos escaping the core, blasts through the star's outer layers and ejects them into space. This is a supernova, one of the most energetic events in the universe. For a few weeks, the dying star can outshine an entire galaxy, releasing as much energy in that brief time as the sun will emit over its entire 10 billion year lifetime. In the extreme conditions of the supernova, nuclei are bombarded with neutrons. Some of these neutrons stick to nuclei, building up heavier and heavier elements through a process called rapid neutron capture, or the R process. This is how elements heavier than iron are made. Elements like copper, zinc, silver, gold, platinum, uranium. These elements can't form through normal fusion because they require energy input. But in a supernova, energy is abundant and neutrons are plentiful. The explosion scatters all the elements the star created during its life, along with the newly forged heavy elements, into the surrounding space. Carbon, oxygen, silicon, iron, gold, all of it is ejected at speeds of thousands of kilometers per second, expanding into the interstellar medium and mixing with clouds of hydrogen and helium. This enriched material, seeded with heavy elements, becomes part of the next generation of stars. The universe's first stars were made only of hydrogen and helium, the products of the Big Bang. But when those stars died and scattered their fusion products, the next generation of stars formed from gas that already contained carbon, oxygen, and other elements. Each generation enriches the interstellar medium further, gradually increasing the abundance of heavy elements over cosmic time. Our Sun is a third-generation star, maybe fourth. It formed from a cloud that already contained about 2% heavy elements, material from stars that lived and died before the solar system existed. That 2% doesn't sound like much, but it's enough to make rocky planets, to form the metals and minerals that compose Earth, to provide the elements necessary for life. Every heavy element in your body came from this process. The carbon was made in the core of a star during helium burning. The oxygen was made in a more massive star fusing carbon and helium. The iron was made in the final moments before a supernova, when silicon fused into iron in the collapsing core. The calcium, phosphorus, sulfur, all the trace elements were created in various stages of stellar evolution and supernova explosions. These elements didn't appear in your body directly from the stars. They had to travel, first through space as expanding supernova remnants, then as part of the interstellar medium, eventually into the cloud that collapsed to form the solar system, then into the disk of material that became Earth, and finally through geological and biological processes into living organisms. That journey took billions of years, and we'll follow it step by step. But first, we need to understand the elements themselves, what they are, and where specifically each one came from. 3 elements form the foundation of life on Earth. Together, they make up about 93% of the human body by atom count. Excluding hydrogen, every protein, every strand of DNA, every sugar and fat molecule, every structure that makes a cell function, is built primarily from these 3 elements bonded to hydrogen. And all 3 were made in stars, through processes that require precise conditions and, in some cases, fortunate accidents of nuclear physics. Carbon is the backbone of organic chemistry, the element that can bond to itself in long chains and complex rings, creating the diversity of molecules that life requires. A carbon nucleus contains 6 protons and, in its most common form, 6 neutrons. It's heavier than helium, but still relatively light, compared to elements like iron or gold. And it forms through one of the more remarkable processes in stellar nucleosynthesis, the triple alpha process. In the core of a star that has exhausted its hydrogen, helium accumulates. When the core contracts and heats to about 100 million degrees, helium nuclei begin to fuse. A helium nucleus is also called an alpha particle, containing 2 protons and 2 neutrons. When 2 alpha particles collide, they can briefly stick together to form beryllium-8, a nucleus with 4 protons and 4 neutrons. Beryllium-8 is unstable. It falls apart almost immediately in about 1/10 of a trillionth of a second. Under normal circumstances, this would be the end of the reaction. Helium would collide and separate, and nothing heavier would form. But if another alpha particle collides with the beryllium-8 during that incredibly brief moment before it decays, the 3 helium nuclei can fuse together to form carbon-12, a nucleus with 6 protons and 6 neutrons. This reaction is extraordinarily improbable. The beryllium-8 exists for such a short time, and the density and temperature have to be just right for a 3rd helium nucleus to arrive and collide in that window. By chance alone, carbon shouldn't form in significant quantities. But there's a resonance, a quantum mechanical alignment, in the energy levels of carbon-12 that dramatically increases the probability of this reaction. The energy of 3 helium nuclei happens to match an excited state of carbon, and this resonance allows the triple alpha process to proceed at a rate fast enough to produce large amounts of carbon. This resonance was predicted before it was measured. Fred Hoyle, a British astronomer and physicist, realized in the 1950s that carbon is abundant in the universe, and that the only way it could be abundant is if there was a resonance facilitating its formation in stars. He predicted the energy level of the resonance, and experiments soon confirmed it existed almost exactly where he said it should be. Without this resonance, carbon would be rare, and complex chemistry, perhaps life itself, would not exist. Once carbon is present in the core, further reactions become possible. A carbon nucleus can collide with another helium nucleus and fuse to form oxygen-16, a nucleus with 8 protons and 8 neutrons. Oxygen is even more abundant in the universe than carbon, and it's the 3rd most common element in your body by mass, after oxygen and carbon. Wait, that's not right. Let me restate. Hydrogen is most abundant by count. Oxygen is most abundant by mass in your body, about 65%. Oxygen is essential for respiration, for releasing energy from glucose, and it's a major component of water, of proteins, of carbohydrates. Oxygen forms in stars more massive than the Sun, in the later stages of helium burning and in subsequent fusion stages. Carbon fuses with helium to make oxygen, and in more massive stars, oxygen itself can fuse with helium to make neon, or with other oxygen nuclei to form silicon and sulfur. The exact abundances depend on the temperature, density, and duration of the fusion stages. But oxygen is reliably produced in large quantities. Nitrogen is slightly different. It's less abundant than carbon or oxygen, making up only about 3% of your body by mass, but it's essential for life. Nitrogen is a key component of amino acids, the building blocks of proteins, and of the nucleotide bases that make up DNA and RNA. Without nitrogen, there would be no proteins, no genetic code, no life as we know it. Nitrogen nuclei contain 7 protons and usually 7 neutrons. Nitrogen can form in multiple ways in stars, but one of the most important is the CNO cycle, a set of reactions that occurs in stars more massive than the Sun. In the CNO cycle, carbon, nitrogen, and oxygen act as catalysts for hydrogen fusion. Protons are added to carbon nuclei, transforming them temporarily into nitrogen and oxygen, before beta decays and further reactions convert them back to carbon, releasing helium nuclei in the process. The net effect is the same as the proton-proton chain that powers the Sun, converting hydrogen into helium. But the CNO cycle proceeds faster at higher temperatures and produces nitrogen as an intermediate product. Nitrogen can also form when helium fuses with carbon-13, a less common isotope of carbon with one extra neutron, producing nitrogen-14 and a photon. And in massive stars, carbon and oxygen fusion can produce nitrogen as well. The details are complex, involving chains of reactions and decays, but the result is that nitrogen is created in stellar interiors and ejected into space when stars die. These three elements, carbon, nitrogen, and oxygen, are the basis for organic molecules. They bond readily with hydrogen and with each other, forming the chains and rings and functional groups that make biochemistry possible. Sugars are carbon, hydrogen, and oxygen. Fats are carbon and hydrogen with a bit of oxygen. Proteins are carbon, hydrogen, oxygen, and nitrogen. DNA is all 4+ phosphorus. The diversity of life is built on the bonding properties of these elements, their ability to share electrons and form stable yet flexible structures. And all of it, every carbon atom in every protein in your body, every nitrogen in your DNA, every oxygen in the water in your cells, was forged in the core of a star billions of years ago. The star burned for millions of years, fusing hydrogen into helium, helium into carbon and oxygen, building up the elements layer by layer. Eventually, the star died, either gently puffing its outer layers into space or exploding violently as a supernova, and those elements were released, scattered into the galaxy, free to drift and mix, and eventually become part of new stars, new planets, and eventually new life. The carbon in your hand was once in the core of a star, held at 100 million degrees, surrounded by layers of burning helium and hydrogen. It was created in darkness, in the crushing pressure of a stellar interior, and it remained there for thousands or millions of years, until the star's death set it free. Then it drifted through space, cooled, mixed with hydrogen clouds, fell into the solar nebula, accreted into Earth, cycled through geology and biology, and now, temporarily, it's part of you. That journey is long, unimaginably long by human standards, but it's the journey every carbon atom has taken. And it's the same for nitrogen and oxygen, for every element heavier than helium. They were all made in stars, through fusion processes that depend on temperature, pressure, and time, and they were all released into space to become part of the next generation of cosmic structures. But carbon, nitrogen, and oxygen are not the heaviest elements in your body. There's calcium in your bones, iron in your blood, phosphorus in your DNA, and trace amounts of dozens of other elements. These heavier elements require even more extreme conditions to form, conditions that only exist in the most massive stars and in the violent final moments of their lives. There's a limit to what normal stellar fusion can create. As stars fuse lighter elements into heavier ones, they release energy, and that energy supports the star against gravitational collapse. But this process can only continue up to iron. Iron nuclei are the most stable, the most tightly bound. Fusing iron into heavier elements doesn't release energy, it requires energy, which means fusion stops being a viable energy source once iron forms. For a massive star, the one that's been fusing hydrogen, helium, carbon, oxygen, and silicon in successive layers. The formation of an iron core is the beginning of the end. The core grows as silicon fusion continues in the surrounding shell, and once the iron core reaches about 1.5 times the mass of the Sun, it can no longer support itself. There's no fusion to generate outward pressure, and gravity wins. The core collapses in less than a second. It's one of the fastest, most catastrophic events in nature. The core, roughly the size of Earth, but with a mass greater than the Sun, implodes. Electrons are forced into protons by the immense pressure, forming neutrons and releasing neutrinos. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. The collapse halts when the neutrons themselves resist further compression through a quantum mechanical effect called degeneracy pressure. The infalling material, still plummeting inward at a significant fraction of the speed of light, hits this suddenly solid core and rebounds. The rebound, combined with the torrent of neutrinos escaping from the core, drives a shockwave outward through the star. This shockwave rips through the outer layers, heating them, accelerating them, and ejecting them into space at thousands of kilometers per second. This is a core collapse supernova, and it's one of the brightest events in the universe. For a few weeks, the dying star can shine with the light of billions of suns, visible across millions of light years. The energy released is staggering, more than the Sun will emit in its entire 10 billion year lifetime, released in a matter of days. In the extreme environment of a supernova, temperatures and pressures far exceed anything that occurs during normal stellar burning. Nuclei are bombarded by floods of neutrons, particles released in vast numbers during the core collapse. These neutrons can be captured by existing nuclei, adding to their mass, building heavier and heavier elements in a process called the R process, for rapid neutron capture. In the R process, a nucleus captures many neutrons in quick succession, faster than it can decay. The nucleus becomes neutron-rich, unstable, and over time it undergoes beta decay, converting neutrons into protons and moving up the periodic table. This process can create elements much heavier than iron, elements like selenium, silver, tin, iodine, gold, platinum, lead, and uranium. Gold, for instance, with 79 protons, cannot form through normal fusion. It requires the rapid addition of many neutrons to an existing heavy nucleus, followed by decay. The conditions for this exist only in supernovae and in the collisions of neutron stars, events where neutron densities and energies are extreme. Every gold atom in the universe, including the gold in jewelry, in electronics, in trace amounts in your body, was created in these violent events. The same is true for many other heavy elements. Uranium, with 92 protons, is produced in supernovae and neutron star mergers. So is thorium, platinum, and most of the elements heavier than iron that exist in nature. These elements are rare because the events that create them are rare. Supernovae happen maybe once or twice per century in a galaxy like the Milky Way. Neutron star mergers are even less frequent. But over billions of years, enough of these events have occurred to seed the galaxy with heavy elements. When a supernova explodes, it doesn't just create new elements. It also scatters all the elements the star created during its life. The carbon and oxygen from helium burning, the silicon and sulfur from later fusion stages, the iron from the core. All of it is ejected along with the newly made heavy elements. The ejected material expands into space, forming a glowing shell of gas called a supernova remnant. Over thousands of years, this shell expands and cools, mixing with the surrounding interstellar medium. The interstellar medium, the gas and dust between stars, is enriched by these supernova remnants. What was once mostly hydrogen and helium now contains carbon, oxygen, iron, and heavier elements. Future generations of stars will form from this enriched material, and they will have higher abundances of heavy elements than the stars that came before. This is how the galaxy's chemical composition evolves over time, through cycles of star formation, fusion, death, and enrichment. The Sun formed from material that had already been enriched by earlier generations of stars. The solar nebula, the cloud of gas and dust that collapsed to form the solar system, contained about 2% heavy elements by mass. That doesn't sound like much, but it's enough to make a difference. Those heavy elements condensed into dust grains, then into planetesimals, and eventually into the rocky planets like Earth. Without heavy elements from previous supernovae, there would be no solid planets, no metals, no minerals, and no life. The calcium in your bones, about 1.5% of your body by mass, was created in a supernova. Calcium nuclei formed during explosive oxygen and silicon burning, processes that occur in the shock-heated layers of a supernova. The iron in your blood, essential for carrying oxygen in hemoglobin, was created in the final moments of silicon fusion before the core collapsed. It was then ejected into space when the star exploded. Phosphorus, which makes up about 1% of your body and is a key component of DNA and ATP, the molecule that stores energy in cells, also comes from supernovae. Phosphorus is created in the oxygen-burning shell of a massive star and released when the star dies. Even trace elements in your body have supernova origins. Iodine, essential for thyroid function, is created through R-process nucleosynthesis. Zinc, important for enzyme function and immune health, is produced in supernovae. Copper, selenium, molybdenum, all of these trace elements that your body needs in small amounts. They all came from the explosive deaths of massive stars. You are made, in part, from violence, not in any destructive sense, but in the sense that the heaviest, rarest elements in your body required extreme energy to create, energies only available in the final moments of a star's life. Those elements were forged in chaos and heat, blasted into space, and eventually, after billions of years and countless transformations, they ended up in you. But supernovae don't just create elements. They also trigger new star formation. The expanding shockwave from a supernova can compress nearby clouds of gas, causing them to collapse and form new stars. In this way, the death of one star can seed the birth of hundreds or thousands of new ones. It's a cycle, death leading to birth, elements scattered and then regathered, the galaxy continuously recycling its material. The elements in your body have been through this cycle multiple times. They were created in stars, scattered by supernovae, incorporated into new stars and planets, and eventually ended up on Earth. Some of them may have been part of earlier planets that were destroyed, or earlier stars that formed and died before the Sun even existed. There's no way to trace the exact path of an individual atom, but we know the general journey, and we know that every heavy element has passed through at least one, probably several, cycles of stellar life and death. And now those elements are part of you, arranged into molecules and cells and tissues, doing the work of life. The calcium in your bones provides structure. The iron in your blood carries oxygen. The phosphorus in your DNA stores genetic information. All of it, every atom, was forged in stars and delivered to Earth through processes that span billions of years and cross vast stretches of space. Understanding this doesn't diminish your individuality or your life. If anything, it deepens the connection, showing that you're part of a story much larger and older than any single human life. A story that begins with the Big Bang and continues through stars and galaxies and planets, through chemistry and biology, to this moment, right now. If you could break your body down into its constituent elements, you'd find a mixture that reads like a catalogue of stellar processes: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, and trace amounts of dozens of others, each with its own origin, its own birthplace in the cores of stars or the violence of supernovae. By mass, about 65%. Most of it is in water, but it's also in proteins, carbohydrates, fats, and DNA. Oxygen nuclei, with 8 protons, form in massive stars during helium burning, and later fusion stages. Carbon fuses with helium to create oxygen, and, in even more massive stars, oxygen itself can fuse with other nuclei to form heavier elements like silicon and sulfur. When these stars die, either as supernovae or through mass loss, they release their oxygen into space, where it eventually becomes part of new stars, planets, and living organisms. Carbon makes up about 18% of your body by mass. It's the backbone of every organic molecule, the element that makes complex chemistry possible. Carbon forms in the cores of stars through the triple alpha process, where 3 helium nuclei fuse together. This process requires temperatures around 100 million degrees and a fortunate resonance in the carbon nucleus that makes the reaction proceed efficiently. Without this resonance, carbon would be rare, and life as we know it wouldn't exist. The carbon in your body came from stars that fused helium in their cores, then died and scattered that carbon into space. Hydrogen is about 10% of your mass, but makes up roughly 60% of your atoms, because hydrogen is so light. Hydrogen nuclei, simple protons, were created in the Big Bang, in the first few minutes of the universe's existence. They're primordial, older than any star or galaxy. The hydrogen in your body has been recycling through the universe for 13.8 billion years. Part of stars, planets, water, and life. But the nuclei themselves haven't changed. They're the same protons that existed when the universe was minutes old. Nitrogen is about 3% of your mass. It's a key component of amino acids, which make up proteins, and of nucleotide bases in DNA and RNA. Nitrogen forms in stars through the CNO cycle, a set of nuclear reactions that fuse hydrogen into helium using carbon, nitrogen, and oxygen as catalysts. Nitrogen is also produced in other fusion processes and is released into space when stars die. The nitrogen in your proteins and your genetic code came from stars that burned hydrogen and helium and then dispersed their products into the interstellar medium. Calcium makes up about 1.5% of your mass, most of it in your bones and teeth. Calcium nuclei with 20 protons form in massive stars during explosive burning phases, particularly in supernovae. Calcium is essential for skeletal structure, but it also plays a role in muscle contraction, nerve signaling, and cellular processes. Every calcium atom in your bones was forged in the extreme heat of a dying star, ejected into space, and eventually incorporated into Earth, and then into you. Phosphorus is about 1% of your mass, but it's critically important. It's part of DNA and RNA, the molecules that store and transmit genetic information, and it's a key component of ATP, the molecule cells use to store and transfer energy. Phosphorus nuclei with 15 protons form in massive stars during oxygen burning and are released in supernovae. Without phosphorus, there would be no DNA, no genetic code, no heredity. Then there are the trace elements, present in small amounts but essential for life. Iron makes up only about 0.006% of your body by mass. But it's critical. Iron is the core of hemoglobin, the protein in red blood cells that carries oxygen from your lungs to your tissues. Iron nuclei form in the cores of massive stars during silicon fusion, the final stage before collapse. The iron in your blood was created in the last moments before a supernova, when a star's core was collapsing and rebounding, and it was scattered into space by the explosion. Zinc, selenium, copper, iodine, molybdenum, these trace elements play roles in enzymes, hormones, and metabolic processes. All of them were created in supernovae through processes like the R process, where neutron capture builds heavy nuclei. Iodine, for example, with 53 protons, is essential for thyroid function, regulating metabolism and growth. It's produced only in the most violent stellar events and exists in your body in trace amounts, a few tens of milligrams, but without it, your thyroid wouldn't function. There are even tinier amounts of heavier elements. Gold, platinum, uranium, all of these exist in your body in vanishingly small quantities. Parts per trillion or less, but they're there. They were created in neutron star mergers and supernovae, scattered across the galaxy, and eventually incorporated into the material that became Earth and everything on it. Every element in your body has a specific origin. Hydrogen from the Big Bang, carbon, nitrogen, and oxygen from stellar fusion, calcium, phosphorus, and iron from supernovae, the heaviest elements from neutron star collisions. You are a mixture, a carefully balanced combination of elements from different places and different times, all brought together through gravity and chemistry into the form you have now. This mixture isn't random. Life requires specific elements in specific ratios. Too little iron, and you can't carry oxygen. Too little calcium, and your bones are weak. Too little iodine, and your metabolism fails. Evolution has tuned life to use the elements that are available, the ones that stars have made abundant. Carbon, oxygen, hydrogen, nitrogen. These are common because stars make them readily. Heavier elements are rarer, so life uses them sparingly, in trace amounts, but often in critical roles. You are a product of stellar nucleosynthesis, a living example of what stars create. The universe spent billions of years building the periodic table, one element at a time, through fusion and explosions and slow accumulation. And now that material is you, briefly, temporarily assembled into a thinking, feeling organism. It's a strange and wonderful thought that the elements in you are ancient, that they've traveled across space and time, that they've been part of stars and planets, and countless other forms before becoming part of you. And they'll continue their journey after you, returning to the Earth, recycling through the biosphere and geology, perhaps eventually becoming part of another star if Earth is consumed when the Sun dies billions of years from now. But for now, they're yours, borrowed from the universe, arranged into the temporary form you call yourself, doing the work of life. After a star dies, whether in a supernova explosion or through the gentler process of shedding its outer layers, the elements it created don't remain in place. They're ejected into space, carried outward by the energy of the explosion or the pressure of radiation, and they begin a journey that can last for hundreds of millions of years. The material expands outward as a cloud of gas and dust. In the case of a supernova, this expansion is violent, with speeds reaching thousands of kilometers per second. The ejected material plows into the surrounding interstellar medium, creating a shockwave that heats and compresses the gas it encounters. Over time, the expanding shell slows as it sweeps up more and more material, and eventually it merges with the interstellar medium, becoming indistinguishable from the background gas and dust that fills the space between stars. This interstellar medium is not empty. It's a thin mix of gas, mostly hydrogen and helium, with about 1% dust made of heavier elements, silicates, carbon grains, ices. The density is extraordinarily low, often just 1 atom per cubic centimeter, far more tenuous than any vacuum we can create on Earth. But space is vast, and over large volumes this thin material adds up. The gas clouds in the interstellar medium are not uniform. Some regions are dense and cold, molecular clouds where temperatures are only a few tens of degrees above absolute zero, and densities can reach thousands of atoms per cubic centimeter. Other regions are hot and diffuse, heated by nearby stars or supernova shockwaves, with temperatures in the millions of degrees, but densities far lower. The interstellar medium is dynamic, constantly being stirred by stellar winds, supernova explosions, and the gravitational pull of passing stars and gas clouds. The elements ejected from dying stars mix with this medium. Carbon atoms drift alongside hydrogen atoms. Oxygen condenses onto dust grains as ice. Iron atoms float freely or bind into tiny solid particles. Over millions of years, the enriched material spreads out, diluting into the larger volume of interstellar gas, but gradually increasing the abundance of heavy elements in the regions where new stars will form. Star formation happens in the densest, coldest parts of the interstellar medium, the molecular clouds. These clouds can be hundreds of light years across and contain enough mass to form thousands or even millions of stars. Gravity slowly pulls the cloud inward, but the process is resisted by turbulence, magnetic fields, and the thermal pressure of the gas. Sometimes an external trigger, a shockwave from a nearby supernova, or the gravitational influence of a passing star, can tip the balance, compressing part of the cloud enough that gravity takes over and collapse begins. Once collapse starts, it accelerates. The denser regions pull in more material, growing more massive and more gravitationally dominant. The cloud fragments into smaller clumps, each collapsing independently. Within each clump, the material falls inward, heating up as gravitational energy converts to thermal energy. Eventually, if the clump is massive enough, the core becomes hot enough for nuclear fusion to ignite, and a new star is born. The material that doesn't fall into the star settles into a disk around it, the protoplanetary disk. This disk is made of gas and dust, the same mix of hydrogen, helium, and heavy elements that the star formed from. Over time, dust grains in the disk collide and stick together, building larger and larger particles. Pebbles form, then boulders, then kilometer-sized planetesimals. These planetesimals collide and merge, growing into planets over millions of years. Our solar system formed this way about 4.6 billion years ago, from a cloud of gas and dust called the solar nebula. That nebula was enriched with heavy elements from earlier generations of stars. Stars that had lived, fused hydrogen and helium into carbon and oxygen and iron, and then died, releasing those elements into space. The material drifted through the interstellar medium for perhaps hundreds of millions of years, mixing with hydrogen clouds before gravity pulled it together into the solar nebula. The atoms in your body were part of that journey. They were created in stars that died before the sun formed, ejected into space as gas and dust, drifted through the galaxy, mixed with other material, and eventually fell into the gravitational well of the collapsing solar nebula. Some of those atoms might have drifted for 1 billion years between the death of their parent star and the formation of the solar system. Others might have been part of multiple stars, created in one, ejected, incorporated into another, ejected again, before finally ending up in the solar nebula. There's no way to know the specific path of any given atom, but we know the general process. Elements are made in stars, scattered into space, mixed with the interstellar medium, and incorporated into new stars and planets. The cycle repeats, generation after generation, each new generation of stars forming from material slightly richer in heavy elements than the last. The solar nebula contained everything needed to build a solar system. Hydrogen and helium, the most abundant elements, made up most of the mass. They formed the Sun and the gas giant planets, Jupiter and Saturn. The heavy elements, only about 2% by mass, condensed into solid particles. Close to the forming Sun, where temperatures were high, only metals and silicates could condense. Farther out, where it was cooler, ices of water, methane, and ammonia could form as well. The rocky planets, Mercury, Venus, Earth, and Mars, formed from the metals and silicates in the inner solar system. The gas giants formed farther out, where ices could condense, and there was more solid material to build large cores that could gravitationally capture hydrogen and helium. The process took millions of years, a chaotic dance of collisions and accretion, but eventually, the solar system settled into the structure we see today. Earth, specifically, formed from countless collisions of planetesimals, rocky bodies ranging in size from meters to hundreds of kilometers. These planetesimals were made of silicates, iron, and other heavy elements, the products of stellar nucleosynthesis. As they collided and merged, they built up the mass of the Earth, and the energy of the collisions melted the planet, allowing iron to sink to the core and lighter silicates to rise to form the mantle and crust. The atoms in your body were part of this process. They were in the dust grains that condensed from the solar nebula, in the planetesimals that collided to build Earth, in the molten rock of the early planet. Over hundreds of millions of years, Earth cooled, solidified, developed an atmosphere and oceans, and eventually became a place where life could begin. But before that, the atoms drifted through space, passengers on a journey that lasted eons, from the cores of dying stars to the birth of a new planet. That journey is part of your history, written into every nucleus in your body. The early Earth was nothing like the planet we live on now. It was a molten, chaotic world, bombarded constantly by planetesimals and asteroids. its surface a sea of magma glowing red-hot under a sky filled with debris. The formation process was violent, driven by countless collisions, each one adding mass and energy, heating the planet further. As Earth grew, gravity began to organize the material. Iron and other heavy metals, denser than the surrounding rock, sank toward the center, forming the core. Lighter silicates, rich in oxygen, silicon, magnesium, and aluminum, rose to form the mantle. This process, called differentiation, took millions of years, and it left Earth with a layered structure: a dense iron core, a thick rocky mantle, and eventually a thin crust at the surface. The core, about 3,500 kilometers in radius, is mostly iron, with some nickel and lighter elements like sulfur and oxygen. It's divided into two parts: a solid inner core and a liquid outer core. The movement of molten iron in the outer core generates Earth's magnetic field, which protects the surface from solar wind and cosmic radiation. The iron in Earth's core, the iron that makes the magnetic field possible, was forged in the cores of massive stars before the Sun existed, scattered by supernovae and gathered by gravity into the material that became Earth. The mantle, extending from the core to within a few tens of kilometers of the surface, is made of silicate minerals rich in oxygen, silicon, magnesium, and iron. It's solid, but flows very slowly over geological timescales, convecting and transferring heat from the core to the surface. The crust, the thin outermost layer, is where we live. It's made of lighter silicates, granite and basalt, enriched in elements like aluminum, calcium, sodium, and potassium. Each of these layers contains elements from different stellar sources. The oxygen and silicon in the mantle came from massive stars that fused helium and carbon. The iron in the core came from supernovae. The aluminum and calcium in the crust also came from supernovae, created in explosive nucleosynthesis. Earth is a concentrated collection of stellar products, gravity having sorted them by density into layers. But Earth wasn't just rock and metal. It also accumulated volatiles, lighter elements and compounds like water, carbon dioxide, nitrogen, and methane. These volatiles couldn't condense in the hot inner solar system during Earth's formation, so where did they come from? The answer, most likely, is asteroids and comets. After Earth's initial formation, during a period called the Late Heavy Bombardment, about 4 billion years ago, the planet was struck by countless icy bodies from the outer solar system. These impacts delivered water, carbon, nitrogen, and other volatiles to Earth's surface. Some water may have been present in the minerals of the planetesimals that built Earth, released as the planet heated and differentiated, but much of it likely came from these later impacts. Over time, as the bombardment slowed and Earth began to cool, the surface solidified into a crust. Water vapor in the atmosphere condensed and fell as rain, accumulating in low-lying areas to form the first oceans. Carbon dioxide and nitrogen filled the atmosphere, creating a thick, greenhouse-warmed blanket that kept the surface warm despite the young sun being dimmer than it is today. The atoms that would eventually become part of you were present on Earth from the beginning, or arrived soon after. Oxygen was in the rocks, in water vapor, beginning to accumulate in the oceans. Carbon was in the atmosphere as carbon dioxide, dissolved in seawater, locked in minerals. Nitrogen was in the atmosphere as nitrogen gas. Calcium, phosphorus, iron, all the elements your body needs, They were there, in the rocks, in the water, waiting. But they weren't in biological form yet. They were part of the geology, the chemistry of a lifeless planet. The transition from geology to biology, from scattered atoms to organized living organisms, took hundreds of millions of years and involved processes we're still working to fully understand. Earth's early oceans were rich in dissolved minerals, a salty, chemical-rich soup warmed by volcanic activity and stirred by tides and currents. Lightning, ultraviolet radiation from the sun, and chemical energy from hydrothermal vents provided energy for simple reactions. Small organic molecules, amino acids, sugars, nucleotide bases began to form, either in the oceans, in tidal pools, or delivered by meteorites that had formed similar compounds in space. At some point, these simple molecules began to organize into more complex structures. Lipid molecules formed membranes, enclosing small volumes of water and creating the first cell-like structures. RNA, or something like it, may have formed and begun to replicate, storing information and catalyzing reactions. Gradually, over millions of years, the chemistry became more organized, more complex, more capable of self-replication and adaptation. By about 3.8 billion years ago, life existed on Earth. The earliest organisms were simple, single-celled, probably similar to modern bacteria. They metabolized chemicals in their environment, extracted energy, grew, and reproduced. They were made of the same elements as the rocks and oceans around them: carbon, hydrogen, oxygen, nitrogen, phosphorus, but organized in a fundamentally new way into self-sustaining, replicating systems. Those early cells incorporated atoms from the ocean, from dissolved minerals, from gases in the atmosphere. A carbon atom that had been drifting as carbon dioxide in the atmosphere might be absorbed by a cell and incorporated into a sugar molecule, then into a protein, then into DNA. An iron atom dissolved in seawater might be taken up and used in an enzyme. Atoms moved from the non-living environment into living organisms, crossing the boundary between geology and biology. And once inside living systems, atoms began to cycle. An organism would grow, incorporating atoms from its environment. It would die, and those atoms would be released back into the environment, available to be taken up by other organisms. This cycling between life and non-life has continued for nearly 4 billion years. The atoms in your body have been part of countless organisms, cycling through the biosphere again and again, never staying in one place for long. Earth became a recycling system, atoms moving through atmosphere, oceans, rocks, and life in interconnected cycles. The carbon cycle moves carbon from atmosphere to ocean, to life, to rock, and back. The nitrogen cycle moves nitrogen from atmosphere to soil, to organisms, and back. The water cycle moves water from ocean to atmosphere, to land and back. Every atom participates in these cycles, sometimes spending millions of years locked in rock, sometimes just days in a living organism, but always moving, always part of the flow. The atoms in your body have been cycling through Earth for 4.5 billion years. They've been part of ancient bacteria, trilobites, ferns, dinosaurs, mammals, fungi, plankton, trees. They've been in oceans, rivers, glaciers, clouds. They've been in volcanic gases, in sedimentary rocks, in soil, in the air. They've traveled across continents, been subducted into the mantle and brought back to the surface. evaporated and rained down, eaten and excreted, grown and decayed. You are borrowing these atoms from Earth's great cycles, temporarily arranging them into the form you have now. Eventually, you'll return them, and they'll continue cycling, becoming part of other organisms, other processes, continuing the journey they've been on for billions of years. There's a rhythm to the way atoms move through Earth, a slow, steady cycling that connects everything to everything else. Carbon, oxygen, nitrogen, phosphorus, all the elements that make up living things. None of them stay in one place for long. They move from air to water, from water to rock, from rock to soil, from soil to plant, from plant to animal, and back again. The path is never quite the same twice, but the movement itself is constant, patient, unending. Consider a carbon atom. Right now, it might be part of a glucose molecule in one of your cells, a fragment of the energy your body is using to breathe, to think, to exist. But this carbon wasn't always yours. A few months ago, it might have been in a leaf on a tree, drawn from the air through photosynthesis, assembled into sugars that the tree used to grow. Before that, it could have been carbon dioxide in the atmosphere, exhaled by someone across the world, or released from the ocean, or emitted from soil as bacteria broke down organic matter. Go back further. That same carbon atom might have been part of a blade of grass a century ago, eaten by a bison, incorporated into muscle tissue, and then returned to the soil when the animal died. Bacteria in the soil consumed the remains, respired some of the carbon back into the air, and incorporated the rest into their own bodies. A root absorbed it. A tree grew. The tree burned in a wildfire, releasing the carbon as smoke. Rain brought it down into a stream which carried it to the ocean, where it dissolved and became part of the carbonate chemistry of seawater. Millions of years earlier, that carbon might have been locked in limestone at the bottom of an ancient sea, compressed from the shells of countless tiny organisms. Tectonic forces pushed the limestone deep into the Earth's mantle, where heat and pressure broke it down. A volcano erupted, sending the carbon back into the atmosphere. It drifted on winds, dissolved in rain, was absorbed by a fern in a carboniferous forest, and later became part of a coal seam buried under miles of sediment. Eventually, erosion exposed the coal. Weathering released some of the carbon. It cycled through the air and ocean, through algae and fish and seabirds and soil, through centuries and continents, until a particular pathway brought it into a plant, into your food, into your bloodstream, and into the cell where it rests now. The journey might have taken hundreds of millions of years, passing through forms and environments you could never catalogue fully, each step governed by chemistry, biology, and chance. This is true for every atom in your body. The oxygen you breathe was likely released by a plant somewhere on Earth within the last few years. But before that, it might have been part of water in the ocean, locked in minerals in rock, or bound in organic molecules in soil. The nitrogen in your proteins came from the atmosphere, fixed into usable forms by bacteria in soil or ocean, cycled through plants and animals, decomposed and re-released, absorbed and built into new life over and over again. The calcium in your bones might have been in the ocean for millions of years, part of the dissolved mineral content of seawater, before it was taken up by a marine organism, incorporated into a shell, settled on the sea floor, compressed into rock, uplifted into mountains, weathered into a river. and carried to the soil where a plant absorbed it. You ate the plant, or ate something that ate the plant, and now that calcium is holding your skeleton together, at least for the time being. Atoms don't stay with you. The cells in your body are constantly being replaced. Your skin sheds. Your gut lining renews itself every few days. Red blood cells are replaced every few months. Even bones, which seem permanent, are continually remodeled, with old material broken down and new material added. The atoms that make up your body today are not the same atoms that made up your body 7 years ago, or even a year ago. You are not a fixed collection of matter. You are a pattern, a temporary arrangement, sustained by a constant flow of atoms passing through. Where do the atoms go when they leave you? Some are exhaled as carbon dioxide with every breath. Some are excreted. Some are shed as skin cells or hair. They return to the environment where they rejoin the great cycles. The carbon you exhale might be absorbed by a tree tomorrow. The nitrogen you excrete might be taken up by soil bacteria next week. The atoms that were briefly you will become part of something else, someone else, seamlessly, without pause. This has been happening for as long as life has existed on Earth. Every atom in your body has likely been part of countless organisms before you. The carbon in your hand might have been in a dinosaur 100 million years ago, in a trilobite 400 million years ago, in a stromatolite 2 billion years ago. The same atom cycling through different forms, different bodies, different ecosystems, across the entire span of Earth's biological history. There's something quietly astonishing about this. You are not separate from the world around you, not separate from the past, not even separate from other living things in any fundamental material sense. The atoms that make you have been everywhere, part of everything, woven into the fabric of life again and again. You are a temporary home for matter that is far older and far more traveled than you are. And it's not just biological cycling. Atoms also move through geological processes on much longer timescales. Carbon gets locked into rock for hundreds of millions of years, then released by volcanic activity or weathering. Oxygen gets bound into iron oxide in ancient rocks, locked away for eons. Water gets subducted into the mantle, held in minerals deep underground, and eventually returned to the surface through volcanism. The Earth itself is constantly reworking its material, mixing surface and interior, old and new, in cycles that operate over hundreds of millions of years. So the atoms in your body have not only cycled through countless organisms, they've also cycled through rock, ocean, atmosphere, and mantle. They've been buried, uplifted, melted, crystallized, dissolved, and precipitated. They've traveled through Earth's geological history, as well as its biological history, moving between reservoirs, changing forms, but never disappearing, never being destroyed. This is the nature of atoms. Once formed, they are essentially immortal. They don't age, don't decay, at least not on timescales that matter for most elements. A carbon atom is indistinguishable from any other carbon atom, whether it formed in a star 7 billion years ago or in a different star 5 billion years ago. It carries no memory, no where, no record of where it's been. It simply exists, moving through space and time, participating in whatever chemical and physical processes it encounters. You are borrowing these atoms. They were here long before you, cycling through Earth's systems. And they will be here long after, continuing their journey through forms you will never see. Your body is not a permanent possession of matter, but a temporary gathering, a place where atoms pause briefly in their long wandering before moving on. There's a continuity in this, a connection that stretches across all of life and all of Earth's history. The atoms that make you have touched everything, been part of everything. They've been in oceans and mountains, in forests and deserts, in bacteria and whales, in rain and rock and air. They've witnessed the whole sweep of Earth's story, though they carry no knowledge of it. They simply move, cycle, transform, participating in the endless exchange of matter that makes the living world possible. And this cycling continues right now, as you listen. Atoms are entering and leaving your body with every breath, every heartbeat, every moment. You are not a static thing. You are a process, a flow, a pattern, held together temporarily by the machinery of life, made from materials that belong to the earth and will return to it, seamlessly woven into cycles that have no beginning and no end, at least not on any timescale you will ever witness. To understand where the atoms in your body have been, you have to stretch your sense of time far beyond anything familiar. The numbers become large, almost abstract, but they're worth holding in mind, even if only briefly, because they reveal just how ancient the materials that make you truly are. The universe began 13.8 billion years ago. That's the current best measurement, derived from observations of the cosmic microwave background and the expansion rate of space. In the first fraction of a second, the universe was unimaginably hot and dense, a soup of fundamental particles with no structure, no atoms, nothing resembling matter as we know it. As it expanded and cooled, protons and neutrons formed from quarks. Within the first 3 minutes, some of these protons and neutrons fused into helium and trace amounts of lithium. But most of the protons remained alone, as hydrogen nuclei. Those hydrogen nuclei are now 13.8 billion years old. Every single one. The hydrogen in your body, mostly in water and organic molecules, is exactly that old. It was made before there were stars, before there were galaxies, before there was any structure to the universe at all. When you drink a glass of water, you are consuming matter that has existed since the universe was 3 minutes old. For hundreds of millions of years after that, the universe was dark. Hydrogen and helium gas drifted through expanding space, cooling, spreading out, with no stars to light it. But gravity was pulling the gas into clumps, slowly, patiently. Eventually, around 100 to 200 million years after the Big Bang, the first stars ignited. These were massive, short-lived stars made purely of hydrogen and helium, with none of the heavier elements that later stars would contain. They burned intensely and died quickly, many of them exploding as supernovae. Those explosions forged the first carbon-oxygen, silicon-iron, scattering them into space. The gas enriched by those first stars collapsed into new stars, which contained small amounts of heavier elements. Those stars lived and died, adding more carbon, more oxygen, more iron to the mix. Generation after generation, the universe's inventory of heavy elements grew. Each new star was slightly richer in metals than the last. A slow accumulation over billions of years. Our sun formed 4.6 billion years ago from a cloud that had already been enriched by multiple generations of earlier stars. The cloud contained hydrogen and helium from the Big Bang, but also carbon, oxygen, nitrogen, silicon, magnesium, iron, and traces of nearly every other element. Some of the stars that contributed to this enrichment had died billions of years before the Sun was born. The supernova that produced much of the iron in your blood might have exploded 6 or 7 billion years ago, long before our solar system existed. Think about that for a moment. An iron atom in your hemoglobin right now might be 7 billion years old. It formed in the core of a massive star, was ejected in a supernova explosion, drifted through interstellar space for hundreds of millions or even billions of years, eventually became part of the cloud that collapsed to form the Sun and planets, was incorporated into Earth, cycled through geological and biological processes for 4.5 billion years, and finally ended up in your bloodstream, carrying oxygen to your cells. That's the journey. That's the history encoded, invisibly, in a single atom. The Earth itself is 4.54 billion years old. In the earliest days, it was molten, bombarded by asteroids and planetesimals, inhospitable to anything resembling life. It took hundreds of millions of years for the surface to cool, for a solid crust to form, for oceans to accumulate. By around 3.8 billion years ago, conditions had stabilized enough for life to begin. Those early life forms were simple, single-celled, but they began the process of incorporating atoms from the environment into biological structures. Carbon, nitrogen, oxygen, phosphorus, sulfur, all the elements that make life possible, started cycling through living organisms. For billions of years, life remained microbial. Bacteria and archaea dominated. They transformed the atmosphere, the ocean chemistry, the surface of the planet. Around 2.4 billion years ago, photosynthetic bacteria began producing oxygen in significant quantities, fundamentally changing Earth's chemistry and paving the way for more complex life. Multicellular organisms appeared around 1 billion years ago. Animals, plants, fungi, all the visible complexity of life emerged only in the last 600 million years or so, a small fraction of Earth's history. During all that time, atoms cycled. The carbon in your body might have been part of a cyanobacterium 3 billion years ago, part of an algae. 1 billion years ago, part of a fern in the Carboniferous, part of a dinosaur in the Mesozoic, part of a mammal in the Cenozoic. The same atoms moving through the tree of life passed from organism to organism, species to species, across the entire evolutionary history of Earth. Most of the atoms in your body have been on Earth for all 4.5 billion years. They've been through everything: the late heavy bombardment, the oxygenation of the atmosphere, the snowball Earth episodes, the rise and fall of supercontinents, the mass extinctions, the slow drift of continents, the churning of the mantle, the cycling of rock and water and air. Every major event in Earth's history, these atoms were here for it, participating in whatever processes were occurring at the time. And they are, in an atomic sense, unchanged. A carbon nucleus today is identical to a carbon nucleus from 4 billion years ago. Atoms don't age, don't wear out. They are passed along intact, unaltered by the passage of time, even as everything around them transforms. The iron in your blood is the same as the iron that existed in Earth's molten interior, the same as the iron ejected from a supernova billions of years before Earth existed. The nucleus, the core identity of the atom, is timeless. It's difficult to hold these timescales in mind. Billions of years is beyond intuitive grasp, But the evidence is everywhere, written in rocks, in fossils, in the light from distant galaxies, in the ratios of isotopes, in the orbits of planets. The universe is old. The materials that make you are almost as old as the universe itself. You are made from some of the most ancient things that exist. Compared to this, human history is vanishingly brief. Homo sapiens has existed for perhaps 300,000 years. Recorded history spans maybe 5,000 years. Your own life is a flicker, decades at most. But the atoms in your body have been here for billions of years, cycling through forms too numerous to count. Part of a story that began with the Big Bang and continues now in you, in this moment. There's a strange comfort in that. You are temporary, but you are made from materials that are not. The atoms that form you will continue long after you're gone, rejoining the cycles, becoming part of new life. New rock, new air. You are not the end of their journey, just a point along the way, one configuration among countless others they have taken and will take. You are very new, made from very old things, a brief pattern in matter that has seen nearly everything the universe has to offer. There's a phrase that appears often, in science, writing, and poetry alike. We are stardust. It's been said so many times that it risks sounding like a metaphor, something poetic, but not quite literal. But it is literal. Every atom in your body, with the single exception of hydrogen, was made inside a star. This is not an analogy. It's a verified fact of nuclear physics and astrophysics. Your body is roughly 65% oxygen by mass. Every oxygen nucleus in you was forged in the core of a massive star, somewhere in the galaxy billions of years ago. Carbon makes up about 18% of your mass. Every carbon nucleus was created through the triple alpha process in a stellar core. 3 helium nuclei fusing together under specific conditions of temperature and pressure. Nitrogen, calcium, phosphorus, sulfur, potassium, all of them came from stars, either from steady fusion during a star's lifetime or from the rapid processes occurring in supernova explosions. Even the trace elements, the tiny amounts of copper, zinc, selenium, iodine, molybdenum that your body needs in minute quantities to function, all of them were made in stars. The heavier the element, the more energetic the process required to create it. Gold, for instance, requires the intense neutron flux of a supernova, or the collision of 2 neutron stars. There are a few atoms of gold in your body right now, perhaps a few trillion scattered across your tissues. Each one of those gold nuclei was created in one of the most violent events the universe can produce. This is verifiable. We know where elements come from because we understand nuclear fusion. We've measured the reactions in laboratories where possible, and we've observed the products. Spectroscopy lets us identify elements in stars, in supernova remnants in interstellar gas clouds. We can trace the chemical evolution of the galaxy over billions of years. Watch how the abundance of heavy elements increases with each generation of stars. The models match the observations. The theory is solid, so when you look at your hand, you are looking at reconfigured stellar material. The calcium in your bones was made in a supernova. The iron in your blood was forged in the core of a massive star. The oxygen you breathe, the carbon in every cell, the nitrogen in your DNA, all of it came from stars that lived, burned through their fuel, and died, scattering their enriched ashes into space. This means you are physically connected to the cosmos in the most direct way possible. Not spiritually, not metaphorically, but materially, atomically. The matter that makes you was once part of a star's interior. It has traveled across light years of space. It has drifted through the cold, dark regions between stars. It has been pulled by gravity into new clouds, collapsed into a new star system, incorporated into a planet, and eventually into you. You are not made on Earth, exactly. You are made from the galaxy. Earth is the assembly point, the place where atoms gathered and organized into geological and biological forms, but the raw materials came from elsewhere, from distant stellar furnaces, from events that took place long before the sun existed. There's a lineage here, a direct physical thread that connects you backward through time. The atoms in your body came from specific stars, now long dead, whose locations in the galaxy you will never know. Those stars might have been hundreds or thousands of light years away from where the sun is now. They might have formed in different spiral arms, in regions of the galaxy that no longer resemble what they were billions of years ago. Those stars themselves were made from gas enriched by even earlier stars. And those earlier stars were made from the primordial hydrogen and helium of the Big Bang, plus trace amounts of carbon and oxygen from the very first generation of stars. The chain goes all the way back to the beginning, an unbroken sequence of matter transformation stretching across the entire history of the universe. You are the current endpoint of that chain, at least temporarily. The atoms in you are pausing, organized into the improbable complexity of a living human body, before they continue onward. You are a chapter in their story, not the conclusion. And you are not alone in this. Every living thing on Earth is made from the same recycled stellar material. The tree outside, the bacteria in your gut, the insects, the fungi, the birds, the fish, all of it is stardust, reorganized and animated by the processes of life. We are all made from the same source, the same generations of stars, the same primordial hydrogen. The differences between species, between individuals, are differences in arrangement, not in fundamental substance. Even the things we don't usually think of as alive are made from stars. The rock beneath your feet, the water in the ocean, the air you breathe. All of it is stellar material. The entire planet is made from the debris of dead stars. Earth itself is a collection of atoms forged in stellar cores and supernovae, gathered together by gravity 4.5 billion years ago into this particular arrangement. The sun is part of this story too. It's currently fusing hydrogen into helium in its core, adding to the universe's helium inventory, though that helium is locked inside and won't be released until the sun dies in about 5 billion years. When the sun reaches the end of its life, it will swell into a red giant, fuse helium into carbon and oxygen, and eventually shed its outer layers into space as a planetary nebula. That carbon and oxygen will drift through space and might, billions of years from now, become part of new stars, new planets, perhaps even new forms of life. You are part of a cycle that operates on cosmic scales. Matter is created in stars, dispersed through space, gathered into new structures, and eventually returned to stars again when planets are consumed or gas clouds collapse. The cycle has been running for over 13 billion years and will continue for trillions more, as long as stars continue to form and die. Right now, you are in the middle of it. You are a living, breathing, conscious arrangement of atoms that were made in stellar furnaces, cooled in interstellar space, assembled on a planet, and organized by biology into something capable of wondering about its own origins. You are matter that has become aware of itself, temporarily, improbably, asking where it came from and what it means. The answer is clear, at least in the physical sense. You came from stars, you are made from their remains. You are stardust, literally, verifiably, undeniably. You will not keep these atoms forever. That much is certain. Over time, the atoms that currently form your body will leave, one by one, returned to the world through breath, through waste, through the shedding of cells. When you die, the process accelerates. Decomposition breaks down the complex molecules that held you together, releasing their constituent atoms back into the soil, the water, the air. What was briefly organized, as you will disperse, rejoin the cycles, and become part of other things. This has always been true. Nothing alive keeps its atoms. Every organism is a temporary configuration, a pattern, sustained by continuous flow. Atoms come in, atoms go out, and the pattern persists for a time, and then it doesn't. This is not tragedy. It's simply the way matter moves through the universe. The atoms themselves will continue. They don't end when you do. A carbon atom that is currently part of your DNA will, someday, be part of something else. Maybe a blade of grass, maybe a bacterium in the soil, maybe dissolved in the ocean, maybe locked in rock for 1 million years before being released again. The atom has no preference, no memory, no awareness of what it was or what it will become. It simply exists, participating in whatever chemical processes it encounters, moving wherever physical laws and chance take it. If you go far enough forward in time, those atoms might leave Earth entirely. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin fusing helium. It will swell into a red giant, expanding outward until it engulfs Mercury, Venus, and possibly Earth. If Earth is consumed, the atoms that once made you will be vaporized, mixed into the sun's outer layers, and eventually expelled into space when the sun sheds those layers as a planetary nebula. They'll drift through space again, just as they did billions of years ago, before the solar system formed. Or, if Earth survives the sun's red giant phase, the atoms might remain on the planet's surface, baked and sterilized, part of a dead, airless rock orbiting a white dwarf. Eventually, over trillions of years, even that remnant might be disturbed by gravitational interactions, ejected from the solar system, or absorbed into another star. The atoms will continue, long after any trace of you, of humanity, of Earth's entire biological history has vanished. They are travelers, and you are just one stop on a journey that may have no end. There's something profound in that. You are temporary, but you are made from things that are not. You are new, but you are built from the oldest materials in existence. You are a brief flicker of organization in matter that has existed for nearly the entire age of the universe and will continue existing long after the last stars have burned out. You are not separate from this process. You are not observing it from the outside. You are it, currently in this specific form. You are the universe arranging itself into a pattern capable of thought, of awareness, of asking what it is and where it came from. You are matter that has become conscious, temporarily, improbably, and in doing so, you are participating in something that may be rare, perhaps even unique in this part of the cosmos. The atoms in your body do not know they are part of you. They have no sense of the billions of years they have existed, the stars they came from, the countless forms they have taken. They are simply there, held together by chemical bonds, organized by the machinery of cells, doing what atoms do. But you can trace the history, understand the origins, recognize the connection. You are the part of the universe that has learned its own story. And the story is one of continuity. There is no break, no separation between you and the stars that made your atoms, between you and the Big Bang that made the hydrogen in your body, between you and the countless organisms that have held these same atoms before you. It's one long, unbroken flow of matter and energy, transformation and recycling, stretching back to the beginning and forward into an almost unimaginable future. You are part of that flow, not separate from it, not exempt from it, not above it, part of it, fully, completely. The same atoms that make you have been part of stars, planets, oceans, mountains, bacteria, dinosaurs, trees, and will be part of things you cannot imagine, in times you will never see. The continuity is perfect. The connection is absolute. This doesn't answer all the questions, of course. Knowing that you are made from stardust doesn't tell you why the universe exists, or what consciousness is, or what, if anything, happens beyond the physical. Those remain mysteries, and perhaps they always will. But it does tell you what you are, in the most fundamental material sense. You are an arrangement of atoms from dying stars, temporarily organized by the processes of life, existing for a brief moment in the vast span of cosmic time. You are ancient and you are new. You are connected and you are unique. You are matter and you are mind. You are the universe, experiencing itself, made from its oldest pieces, aware of the journey, even though the journey has no destination, no purpose, no endpoint that we know of. The mystery is not where you came from. That we understand. The mystery is what it means to be here, briefly made from such old and well-traveled materials, capable of knowing the story and wondering what comes next. And maybe that's enough, to know that you are part of something vast, something ancient, something that began long before you and will continue long after. To know that the atoms in your hand have been part of stars, have drifted through space, have witnessed the slow unfolding of cosmic history. To know that you are not separate from the universe, but woven into it, materially, physically, completely. You are stardust, arranged into a form that can look up at the night sky and recognize itself in the light of distant suns. You are the cosmos made conscious, briefly, improbably. You are ancient atoms, borrowed for a moment, soon to continue their journey. And for now, for this brief moment, those atoms are you.